All right, here's part two of limits at infinity, or involving infinity. Let me drag this up. There we go. So I'm just going to go through some examples and explain my thinking. And what I'm going to focus on now is how you can tell whether it approaches positive or negative infinity in some of these cases. Okay, so let's look at number 4. Number 4, like I said before, the plus 1 doesn't mean anything as you go towards infinity. The minus 3x even doesn't mean anything. So really, this problem boils down to square root of x squared over 2x. And everybody knows the square root of x squared is just x. It's positive, and that's something to watch out for. But this would be, when it boils down to it, after you get rid of all the nonsense, it boils down to an equal weight one, which, remember, when you're done canceling, it's just the coefficients. Now be careful, don't just write your answers 2. There is a 2 left over, but it's in the bottom. So it's really 1 over 2, also known as 1/2. So that's a horizontal asymptote. You should be careful, though, whether or not this is positive. And I always like to, in every one of these problems where I'm giving an answer, whether it's infinities or a real number, I like to double check in the original problem, would my fraction have been positive or negative? So the top, if I put in positive infinity and square something and square root it, the top is going to be positive, big positive number. And the bottom, if I put a positive infinity, well, 2 times a positive infinity is still a 2, or a huge positive number. So I have a positive over a positive, which is why I'm leaving my answer as positive 1/2. Then we go down here, check this one out. See how I'm careful on this, how I'm going to negative infinity on this one. So the problem's going to look the same, right? The 1 doesn't mean anything. The minus 3x doesn't mean anything. It's going to approach negative infinity. And if you're not careful, you will treat this problem the same and say, okay, well, it must be x over 2x, which simplifies to be 1/2. And you might think that's the answer because you're like, well, I don't have anywhere to plug in a negative infinity, so it's good. Not true. Because if you go back to the original problem, and this is the common sense part of these, which I kind of like, and you put a negative number in here, what happens when you square a big negative number? You get an even bigger positive number. And then you square root that, and you're back to the number, but now it's positive. So the top has to be a positive. The bottom, 2 times a giant negative number, is still a giant negative number. You have a positive over negative, which means my end answer is not 1/2, but it's negative 1/2. So that's kind of sneaky. Let's not do number 6 yet. We're not getting into the trig stuff for a little while. Okay, we attack number 7. This approaches positive infinity, right? It's always important to notice that. So once again, this doesn't matter. This doesn't matter. It behaves like 2x over x. Remember, absolute value of x is still just x. It's positive, though. Always positive. So this is another equal weight problem where the answer is 2 over 1. And then I need to double check, should it be a positive 2 or a negative 2? If I put in a positive infinity, I'm just pretending, a huge positive number and double it, the top is still, I'll put it up here, the top is positive. If I put in a huge positive and absolute value, the bottom is positive. So positive over positive leaves me with that same answer. If this would have said negative infinity, you would have had a negative on top and a positive on the bottom, which would have changed this. All right, next one, huge negative number. Okay, so if you put in, remember, oh, it's sneaky. Ooh, look out. Those don't matter. See how it's sneaky because the highest power is right here. So the highest power is x squared. This one's a little weird because you have a fraction and a fraction. So it might help you to notice if you put a huge negative number in here, in the bottom, Like imagine 1 divided by 1,000,000. It's going to be almost 0. Okay, so it's like saying a huge number on top, positive number, right? Call it like an infinity on top divided by a 0 on bottom. Because this thing right here, 1 divided by infinity is worth 0. It's weird, but just try it a couple times. Try 1 divided by 100, 1 divided by 1,000, 1 divided by 1,000,000. It gets closer and closer to 0. If you take infinity divided by 0, it is infinity. I know, it sounds weird. But basically, anytime you have 0 on the bottom, you have a vertical asymptote. So you have a vertical asymptote, or it's going to infinity. You have a tiny number on bottom and a big number on top. So if you need help with that idea, this is very conceptual. Imagine taking a big number on top divided by a tiny number on bottom. It gets even bigger. So this one's going towards infinity. Now I have to double check, should it be positive or negative? So watch out for this. If I plug a negative in the bottom, it's close to 0, but it's a tiny, tiny negative number. So the bottom of my fraction is negative. The top of my fraction is, you're putting a negative in here and squaring it, so it makes it positive, but there's a negative 5 times it in front, which makes it negative again. If you have a negative or a negative, your answer is positive. You could just try that with numbers. This is a case where your head might be doing flips right now, so you might want to just go to the advice here and plug in a very large or very small number to determine the sign. So maybe you use this problem they gave you originally and type in negative 1,000 and see what happens. You'll see what the sign of the answer is. Okay, and then this one says find a power function to model end behavior. Basically, that's like the step I keep doing of reducing this. Okay. You know how like you do end behavior and sometimes you get a horizontal asymptote? Well, if you get a top heavy one, you can get a power function that the graph behaves like way out to the right and way out to the left. So basically you're still treating this like one of the problems before, where these become less important because they're all really small in comparison to these when you go to positive infinity or negative infinity. And the graph ends up behaving like x to the fourth over negative x to the fourth over 5x squared. And I'm going to simplify that to be, okay, x squared here cancels with 2 of those. And it's going to behave like negative x squared over 5. Which, if you think about that, that's a quadratic, right? Like if I wrote, if I just wrote f of x is negative x squared over 5, it's going to be, a graph that looks sort of like this. Now, will that original graph look like this? No, but it will behave like this graph way, way out to the right and way, way out to the left. So in the end, it's going to approach these lines that go on forever. It's just they won't happen right away. So that's kind of weird. But find a power function. It's basically get the biggest powers and reduce them. And this describes what your graph behaves like and behavior model. That's what your graph will look like way down the road. It's not even until you get past the millions for your x's or negative million will it start acting like this graph. But it will. And that's kind of crazy. Basically shows you how much power these highest exponents have, how much control over the graph. Then you get here. I'm going to do the same thing again. I'm going to reduce those because these don't matter. Remember, these don't matter only because we're going towards infinity and negative infinity. They would matter until we get out really, really far. So if I cancel an x off top and bottom, my graph behaves like 4 over x. This is my behavior model, it actually, it's a bottom heavy graph. So if it's bottom heavy, my limit as x goes to infinity or negative infinity, it's going to be 0. Because you have a bottom heavy graph, it always ends 0. So this one has horizontal asymptote, and it's y equals 0. That's your horizontal asymptote. This one didn't have a horizontal asymptote because it was top heavy, so it's controlled by here. And the last one is, it's just, we did vertical asymptotes in our continuous thing, and you always look for when the denominator equals 0. Well, this says another way to tell if you have a vertical asymptote is if you do the limit as x approaches a, and the limit is positive infinity or negative infinity. Oops, you can't really see that. That's from the left and from the right. So if you do it from the left, and it goes to positive, or sorry, that's the right. If you go from the right and it's positive or negative infinity for your limit, and you go from the left and it's positive or negative infinity for a limit, you got yourself an asymptote. Same deal here. This graph is going to have a hole in it, or not a hole, an asymptote, because I look at the denominator and I'm like, oh, when x equals 2, it's a vertical asymptote. How do you know? You could double check. This seems excessive, but you could say as I approach 2 from the left of this graph, you could either look at the graph, use the graph of this guy, and see what happens. Let's see what that looks like. I'm going to pause for a second, type it in. Alright, so this is what it is. I'm going to type it in with parentheses. If you don't use parentheses, you'll get that wrong. Zoom 6, and we'll take a look at this graph. Okay, so looking at the picture, from the left, what's this graph doing? It's going down forever. So from the left, it's negative infinity. Okay, let's check out the other one. Never mind, we're not checking out that one. That's a greatest integer kind of problem. Find the vertical asymptotes. So for this problem, kind of like when we did continuous or not continuous, x plus 2, x minus 2. So I have vertical asymptote at x equals 2 and x equals negative 2. So I got that, found the vertical asymptotes because I just look for when the bottom's 0. And then I'm supposed to describe the behavior to the left and right of each vertical asymptote. And that's hard to do without a calculator. You can do it in your brain. You can do the limit. I mean, it depends if you like using your brain or not. The limit is x. Let's just do this first one. X approaches 2 from the right. And the limit as x approaches 2 from the left. We'll look at the graph in a second, but I want to see if your brain works. Okay, imagine a number slightly bigger than 2. Let's call it 2.01. If you put a 2.01 in here, it makes that number positive, right? If you put a 2.01 in here, it makes that number positive. It's tiny, but it's positive. So what's the denominator going to be? Positive. I guarantee it's still going to be a vertical asymptote, but it's going to keep it positive. So my guess from the right would be, since it's a 1 over a tiny positive number, it goes to positive infinity. Now if I look at the graph and check it, look, I'm approaching 2 from the right. Guess what it does? It goes crazy upward, but I don't just know it's divided by 0. I know it's going to be a positive number. If I come from the left, okay, imagine this. I come from a number slightly smaller than 2, which is like 1.99. That would be a number bigger than 0, and this would be a number smaller than 0. So you have a positive times a negative, which results in negative infinity. And you can do that, or you could use the graph. So for my other two, from the left, it basically reverses these. From the left, it's up, and from the right, it's down. So you can do that for the other two. All right, hope you enjoyed. Talk to you later.